Namaste and welcome everyone. Grab your notebooks, sharpen those pencils, and pay close attention because today we are going to have an absolutely fantastic geometry session. The chapter heading is right here, I am up and down and round and round. We're diving deep into the beautiful, mathematically perfect world of circles. Let's get started, shall we?
Chalo, here is what we are mastering today. First, circles in our world. Then, the definition of a circle. Third, chords and their angles. Fourth, perpendicular bisectors. Fifth, cyclic quadrilaterals. And finally, let's solve some questions.
Section 1. Circles in our world. Before we draw any equations or start stressing over formulas, I want you to just look at the world around you. Humanity has always been absolutely fascinated by the natural shapes we see every single day. Look at this. On one side, a bright full moon. On the other, the sun during a total solar eclipse. Breathtaking, right? Even in ancient cave paintings like the ones in Gudahandi in Odisha, we see these exact geometric patterns being drawn by our ancestors. Nature is literally filled with them. Think about when raindrops hit a puddle of water, or the cross-section of a plant stem, or even the face of a sunflower. They all share this unbroken, perfect shape. Section 2. The definition of a circle. So we're now going to turn these beautiful natural observations into a formal, rigorous mathematical concept. By definition, a circle is the set or locus of all points on a plane that are equidistant from a given point, which we call the center. Simple funda, right? Imagine you're standing at a spot on an empty field. That is your center, and you are holding a rope of a fixed length. If you walk all the way around, keeping that rope perfectly tight, every single footstep you take is a point on that circle. That's all it is. Let's do a quick high-energy recap of the essential parts on our whiteboard, the stuff you definitely need to remember. We have the center, our starting anchor point. The radius, which is the distance from the center to any point on the circle, just like that tightrope we talked about. Then we have a chord, which is simply a straight line segment joining any 2 points on the circle. And what if that chord decides to go right through the center? Boom, it becomes the diameter. And keep this in mind for later. The diameter is the absolute longest chord possible. Section 3. Chords and their angles. Okay, so we know what a chord is now, but how do these straight lines that cut across the circle actually interact with our center point? Here's a little Socratic question for you. Think about it, yeah? Do equal chords make equal angles at the center? Imagine I take a piece of string, pull it tight across a wheel to make a chord, and measure the angle it makes at the center. Then I take that exact same string and place it somewhere else on the very same wheel. Will the angle at the center still be exactly the same? Yes, they absolutely do. Theorem 2 clearly states, equal chords of a circle subtend equal angles at the center of the circle. Now, what's really interesting is the why. How do we prove it? Well, imagine 2 triangles formed by these 2 equal chords, and the radii connecting their ends to the center. The radii are all equal, right? That is the very definition of a circle. And the chords are equal because we just said they are. So by the SSS, side-side-side congruence rule you learned in earlier classes, those 2 triangles are exactly identical. Therefore, their corresponding angles at the center must be equal. Absolutely clear? Perfect. Section 4. Perpendicular bisectors. Let's look a little closer at the distances between these chords and the circle's center. If you draw a very long chord, where is it sitting? It's sitting right up close to the center. The longest chord, the diameter, passes right through it. But if you draw a very short, tiny chord, it gets pushed far, far away towards the outer edge of the circle. The clear rule here is simple. Given 2 unequal chords, the longer chord is always closer to the center. Now, what if we have just 2 points? Let's call them A and B. How many circles can pass through both of them? The answer is infinitely many. You can draw huge ones, you can draw tiny ones. But here is the magic trick. The centers of all those circles will lie exactly on the perpendicular bisector of the line joining A and B. Why? Because every point on a perpendicular bisector is, by definition, equidistant from the 2 endpoints. This is a very important foundation that sets up our next big theorem. Which brings us to Theorem 1. There is a unique circle passing through 3 non-collinear points. If you have 3 points, A, B, and C, that aren't just sitting in a straight line, you can draw exactly one circle that hits all 3. Why? Because the perpendicular bisector of line AB and the perpendicular bisector of line BC will intersect at exactly 1 point. 2 lines can only cross once, right? That unique intersection is your center, what we call the circumcenter. And that gives us exactly 1 unique circle for any triangle.
It's brilliant.
Section 5, Cyclic Quadrilaterals. This is our final theoretical concept for today before we get our hands dirty with some real math problems. So the crucial point is understanding what the word cyclic means here. A cyclic quadrilateral is a four-sided shape where all four vertices, all four corners, are perfectly inscribed on a single circle. Imagine drawing 4 points anywhere on the boundary of our perfect circle and connecting them with straight lines. That shape you just made, that is a cyclic quadrilateral. And here is the golden rule for these shapes, a rule you absolutely must memorize for your exams. In a cyclic quadrilateral, the sum of opposite pairs of angles is exactly 180 degrees. If you take the top left angle and add it to the bottom right angle, boom, 180 degrees. Conversely, if opposite angles of a four-sided shape add up to 180, it must be cyclic. It's literally like a magic key for solving geometry puzzles.
Section 6. Let's solve some questions.
Now, let's apply our brains. Theory is wonderful, but mathematics is all about solving. Let's tackle some end-of-chapter exercises step by step together. Here is our first question, straight from the textbook. A chord is 5 centimeters away from the center. The radius of the circle is 13 centimeters. What is the length of the chord? This is a classic exam question. You'll see this everywhere. Let's break it down into logical steps. Step 1. Always draw the figure. Draw a line from the center straight down to the chord. That is your 5-centimeter distance. And remember a key property we learned. A line from the center perpendicular to a chord bisects it. Then draw the radius from the center to the end of the chord. That is 13 centimeters. You have just constructed a right-angled triangle. Step 2. Use the Baudhayana Pythagoras theorem. The square of the hypotenuse minus the square of the other side gives us the square of the base. 13 squared is 169. 5 squared is 25. 169 minus 25 is 144. The square root of 144 is 12, so half the chord is 12 centimeters. Step 3. Don't stop there. Double the result. 12 plus 12 is 24 centimeters. The full length of our chord is 24 centimeters. Step by step, it's that easy. Let's do another one. Rapid fire this time to test your memory on shapes. Question 2. ABCD is a cyclic quadrilateral. If angle A is 75 degrees, what is the measure of angle C? We just learned this rule minutes ago. Opposite angles in a cyclic quadrilateral sum to exactly 180 degrees. Angle A and angle C are opposites, so 180 degrees total minus the 75 degrees we already have gives us 105 degrees. Angle C is 105 degrees. See? If you just know the rules, geometry is just simple arithmetic. I'll leave you with one final provocative question to ponder, right from the end of the textbook exercises. Is there any chord of a circle that is longer than its diameter? Think about the very definition we started with today. Think about how longer chords move closer and closer to the center until they finally pass right through it, becoming the diameter. Can anything stretch further across a perfect circle than the line passing through its very heart? Keep exploring, keep practicing those geometry sums, and I'll see you in the next explainer.